Besides the Sun, our Doradus is the largest star in the Earth's night sky. It is located in the constellation of Dorado, and it can only be seen from the southern hemisphere of Earth. In 2024, scientists for the first time in history observed the surface of this star in detail, discovering that scorching plasma is boiling and forming huge bubbles. The radius of this star is even close to 300 times that of the Sun. However, although our Doradus is the largest star in the night sky, it is far from the largest star in the universe. Until recently, the title of the universe's largest star belonged to UY Scuti. In 2012, astronomers used a very large telescope in Chile to measure three supergiant stars near the center of the Milky Way galaxy, including UY Scuti. Initially, its measured radius was about 1,708 times that of the Sun. But don't think, this star is just simply over 1,700 times larger than the Sun. Let me explain what this really means. For example, imagine two cubes in front of you. Among them, the side length of the white cube equals 1 solar radius, while the side length of the gray cube is 2 solar radii, although the side length of the gray cube is only twice that of the white one. However, its volume can accommodate 8 white cubes. This principle applies to any other three-dimensional object, including celestial bodies like stars. This means that, if scientists calculated correctly, in theory, UY Scuti could contain nearly 5 billion suns. However, the latest measurements in 2023 showed that the radius of this star is actually only 909 solar radii. Thus, in 2024, the title of the universe's largest star fell to WOHG 64. Its radius is over 1,500 times that of the Sun. This giant star is located in the Large Magellanic Cloud, a neighbor galaxy of the Milky Way, about 160,000 light-years from Earth. If we were to replace the Sun with it, then its extent would surpass the orbit of Jupiter. This star is surrounded by a huge cloud of dust and gas, with intense stellar winds constantly blowing this material away. The total mass of this dust cloud is roughly equivalent to 9 times that of the Sun, extending a full light-year. Actually, among known stars, there is one much larger than WOHG 64. It is the red supergiant Stephenson 2-18, with a radius reaching 2,150 times that of the Sun. But despite its enormous size, scientists are not convinced of its status. And the reason behind this is, its existence violates known laws of physics. Its radius exceeds the so-called Hayashi limit. Typically, a star, to prevent being torn apart by the internal plasma pressure, or crushed into a white dwarf by its own gravity, must maintain a state of hydrostatic equilibrium, that is, a delicate balance between inward gravitational force and outward pressure. This balance determines the relationship between the star's mass, radius, and temperature. However, Stephenson 2-18 breaks two of these rules. Its radius and temperature both exceed the theoretical limits. The maximum temperature for such stars should be around 3,500 Kelvin, while Stephenson 2-18's surface temperature is only 3,200 Kelvin, lower than the coldest known supergiants. This indicates that either the measurement data for it is incorrect, or our physics theories are not yet complete. Therefore, it is currently still recognized that WOHG 64 is the largest star in the universe. But in the universe, the standards for measuring stars include not only size, but also factors like their luminosity and mass in space. For example, the star classified as a hypergiant, R136A1, although its radius is only about 42 times larger than the Sun's, it is considered one of the most massive, luminous, and hottest stars in the universe. Its mass is almost 200 times that of the Sun, making it currently the second most massive star known in the universe. But this title might not last long, because massive stars lose their material through powerful stellar winds. For R136A1, the stellar wind speed is a stunning 2,600 kilometers per second. Therefore, this star loses over 3,000 trillion tons of mass every second. Scientists estimate that since its formation, it has already lost about 35 solar masses. Furthermore, its luminosity is equally astounding, being almost 4.7 million times that of the Sun. If our Sun reached this brightness, the temperature on Earth's surface would soar to a terrifying 16,200 Kelvin, almost 3 times the current surface temperature of the Sun. Nevertheless, its brightness in the universe only ranks 7th. The title of the brightest star belongs to the star Godzilla from the Sunflower Galaxy, Messier 63. Its luminosity is 255 million times that of the Sun, which is simply unbelievable. However, in the contest for the hottest star, our 136A1 easily wins over this Godzilla star. Its surface temperature is about 46,000 Kelvin, roughly 1.5 times that of the Godzilla star, and 8 times the temperature of the Sun. But even so, it still can't compare to the true king of high temperatures. This star with only half the Sun's radius is WR102. It might be one of the most dangerous stars in the universe. Its extreme stellar wind is stripping away its own material at hundreds of millions of times the rate of the Sun. This violent stellar wind, along with intense ultraviolet radiation, compresses and ionizes the surrounding interstellar matter, forming a bubble-like nebula around the star. And all this stems from its extremely high temperature, which can even reach around 200,000 Kelvin. If our Sun became this hot, it would not only evaporate Earth's oceans and atmosphere, but even most chemical elements on Earth would be vaporized. Scientists speculate that WR102 is nearing the end of its life, and may soon end its life in a supernova explosion. When that happens, its title as the universe's hottest star will also be passed on. In the universe, besides those giants thousands of times larger than the Sun, there are also some stars famous for being the smallest. For example, this star with a very long name, EBLMJ0555-57b. Its radius and mass are only 8% of the Sun's, and it is the smallest star known to humans, capable of sustaining nuclear fusion in its core. Most incredibly, it is even smaller than Jupiter. So why doesn't the larger Jupiter become a star? Although the mass of this gas giant planet is twice the sum of all other planets in the solar system, it is only 1/1000 th the mass of the Sun, far insufficient to trigger its own nuclear fusion reaction. But not all stars follow this rule. For example, another star with a long name, PSR B0943+10. It might be the most incredible object in the universe, a pulsar made of neutrons, possessing an extremely strong magnetic field, rotating once every 1.1 seconds. And most surprisingly, the radius of this pulsar is only 2.6 kilometers, less than 1/4,000,000 th of the Sun's radius. Even though it is so tiny, the radiation it emits is enough to instantly destroy all life on Earth. However, its rotation speed will gradually slow down in the future until it stops, and its temperature will continuously decrease, eventually leaving only a dead core. In the Ursa Major constellation in the northern sky of Earth, there is a supernova named IPT F14HLS. In 2014, scientists observed this supernova explosion located over 500 million light-years from Earth. Initially, it seemed like just an ordinary astronomical event. However, this outburst happened again and again repeatedly. Over the next 1,000 days, scientists observed 5 brightness peaks, each peak's intensity equivalent to a full supernova explosion. Even more puzzling, when they checked historical data, they found that this star had already exploded once, 60 years ago. What exactly is going on? Scientists still don't have a clear answer. One hypothesis suggests that the star's core might have produced some antimatter. Whenever this antimatter comes into contact with normal matter, annihilation occurs, triggering a phenomenon similar to a supernova explosion. Perhaps in the future, new discoveries will be able to unravel this mystery. But one thing is for sure, 400 ms. The more we explore the universe, 400 ms, the more stars that break new records we will discover. 400 ms. For example, a type of star known as 400 ms, a Thorned Zitko object. 400 ms. According to scientists' speculation, 400 ms, at the core of some red supergiants, 400 ms. It might not just be compressed helium, 400 ms, but there could also be a full-grown neutron star. 400 ms. This type of object, 400 ms, might form from 400 ms, a collision between a red supergiant and a neutron star. 400 ms. It is a hypothetical star type proposed 400 ms by theoretical physicist Kip Thorne and astrophysicist Anna Zitko in 1977. 400 milliseconds. Later, the Clay Christmas Telescope in Chile 400 ms discovered the first potential Thorn Zitko object 400 ms and named it HV 2112.400 milliseconds. However, for years later, 400 ms, new research 400 ms, refuted the conclusion that a neutron star existed inside this red supergiant 400 ms, because such objects require 400 ms, high concentrations of lithium, molybdenum, and rubidium, but after detailed observation, it was found that the elemental abundance in this star did not reach the required levels. Yet in the same year, scientists discovered a new candidate, HV 11417, but its identity has not been confirmed yet. In 2023, the James Webb Space Telescope discovered several candidate dark stars, potential dark matter objects. They are JHGS Z13-0, JHGS Z12-0, and JHGS Z11-0. These objects are extremely distant from Earth, so the light we see from them now was emitted 13.8 billion years ago, about 200,000 years after the Big Bang. If they can be confirmed, it would be a major breakthrough. After all, the existence of dark matter is still an unsolved mystery. According to theory, dark stars might be formed from the collapse of hydrogen and helium in the core of a protostar. In the galaxies of the early universe, dark matter particles would collide and annihilate, triggering chain reactions within gas clouds. These processes would heat the hydrogen-helium cloud and eventually give birth to stars. The temperature of dark stars might be similar to the sun's, but their mass is 1 million times that of the sun, and their brightness is 1 billion times that of the sun. Theoretically, such stars would collapse into a supermassive black hole at the end of their lives. Currently, scientists just need to find one key piece of evidence to confirm whether these three objects are dark stars, a breakthrough in the electromagnetic spectrum, such as detecting a specific helium isotope. In the universe, there is also a special type of object called a black dwarf. It is the final stage of evolution for small to medium mass stars like the Sun. Currently, scientists have not found any black dwarfs. The reason might be that the universe is still too young, and no star has had enough time to evolve to this stage. When a star the size of the Sun stops internal nuclear reactions, it will shed its outer material, forming a nebula, and leave behind an extremely dense white dwarf at its center, with temperatures between 4,000 and 150,000 Kelvin. But since the core of this star is already dead, unable to maintain its temperature, it will slowly cool down, eventually becoming a cold, dense black dwarf. And this cooling process takes about 1,000 trillion years, but our universe is only 13.8 billion years old. This is why black dwarfs have not appeared yet. Having talked about so many types of extreme stars today, which one interests you the most? In the vast and boundless universe, there are countless surprises still hidden, waiting for us to explore and discover.